Hello and welcome to our last lesson of differential equations, Unit 5. So today we're going to be talking about applications of differential equations, and a lot of this is going to deal with position, velocity, acceleration, things we've talked about before, but now we're going to kind of examine through the lens of differential equations. So we know that the constant acceleration due to gravity is negative 32 feet per second squared, and which is also negative 9.8 meters per second squared, excuse me. And what we want to do is first solve this differential equation to find an equation for the velocity function. So we can do that. We have dv over dt is equal to negative g. Well, we can rewrite that as dv is equal to negative g dt, right? And then we integrate, of course. So we get v of t is equal to negative g of t plus c sub 1. Well, what is c sub 1? C sub 1 is our initial velocity. All right. Okay, so we have solved we've solved this differential equation to find the velocity function, and now we're going to solve the velocity function to find position. So we're going to take the integral of ds. Well, before I even do that, I should get back to here. So we know that the velocity function dv over dt is equal to ds over dt, right? Which is equal to, we know it's equal to negative gt plus c sub 1, okay? So now we want to use this information to find position. So ds is equal to negative gt plus c sub 1 dt. We're going to integrate both sides. So we get s of t, you see this, okay? S of t is equal to negative g over 2 t squared plus c sub 1 t plus c sub 2, okay? Well, c sub 2, that's going to be our initial height, kind of our initial position. So we can actually rewrite this whole thing as s of t is equal to negative g over t quantity squared plus v sub naught t, our initial velocity. Remember, c sub 1 is our initial velocity, plus s sub naught, that's our initial height, okay? So that sub naught means, or sub 0 means that that's initial. Okay, so let's actually do some math here. Let's talk about it. So a person wearing a squirrel suit falls from the top of a 558-foot building. How many seconds elapsed before they hit the ground? Okay, well, we know that their velocity, dv over dt, is going to be equal to negative 32t, and we can solve for that. So dv is equal to negative 32t dt. We're going to integrate both sides. So we end up getting, where did it go? Yeah, so dv, this is actually going to become, when we integrate velocity, we're going to get position. So s of t is going to be equal to negative 16t squared plus c. Well, they fall from the top of a 558-foot building, so at s of 0, at time equals 0, negative 16 times 0 squared plus c is equal to 558, right? So c is equal to 558. So s of t is equal to negative 16t squared plus 558, right? And we want to know their position when they actually hit the ground. Well, when they hit the ground, their position is going to be at 0, so I can set this equal to 0. So I end up having negative 16t squared is equal to negative 558. So t squared is equal to, let's see, 558 divided by 16. T squared is equal to 34.875. So t is about 5.906 seconds. Okay? All right, so there's our first question. We found how long did it take him to hit the ground? About 5.9 seconds. Okay, and let's move on to our second question. With what velocity in feet per second did they actually hit the ground? Well, we can calculate our velocity. Our velocity at And you can use 5.906, or you can actually use the exact value here. I'll use the exact value, why not? The square root of 558 over 16 is equal to negative 32 times the square root of 558 over 16, which is equal to negative 32 times second square root of 558 divided by 16 is equal to negative 188.976 feet per second. So that's the velocity that they hit the ground with. Wow, sounds very painful. Okay, so let's turn the page here.